All right, welcome to ECGR 4101, 5101, Lecture 2. All right. And people are giggling here because what I did is I'm covering some of Lecture 1. I just finished it, and now I'm going into Lecture 2, and I'm going to cover it for the rest of today. So, if you think about what is the world about microcontrollers? What is everything that you could ever think of that you would ever need for a microcontroller? So let's take a look at this. So think about this. If we have a piece of silicon, and this piece of silicon is going to be put on a piece of plastic, and then on this piece of plastic I'm going to pull off these wires off the side, right? All right, so I've got this is not to scale, by the way, all right? If we were to say, how big is this compared to a coin? So this is, we'll call this a dime, all right? You could pull a dime out of your pocket, or was it in India, rupee? That's not the smallest one, is it? A paisa? I'm going to learn this. P-A-I-S-A. A paisa. All right. Is that a really tiny coin? Okay. Smaller than a U.S. penny? All right. So we'll go. So now you undergrads, you're learning something too, right? This is what is it? 1/100th of a rupee? Yeah. All right. Probably cabinet. So, does everybody know how they manufacture chips, by the way? That would be something to cover as well. Yeah, I'll cover that. What the heck? I'll do it on the sheet of paper here because then it could be saved. Everybody know what silicon is? What is it? Sand. All right. More or less, all right? There's a lot of processing that goes in. Actually, sand, when you melt it and mix it with something else, is glass. But it's pretty darn close. So all of you who have been in our undergraduate courses had better know how you make silicon, a semiconductor, and I'm not going to cover it in this class. But after they make the wafers, and by the way, they make they get big silicon ingots. Looks like a big giant cucumber, but it's more like an Italian sausage or hard salami. And then they slice small little pieces off, and you get a wafer, and that's just a single slice out of this. And then they go through their processes where, using any sort of manufacturing processes, they actually put the semiconductor material on the chips themselves, and they usually have them arrayed in or organized in arrays, squares. Then they're tested on the wafers, and then those that are good are cut off the wafer. Then they put it on a piece of plastic, and then once it's on the piece of plastic, then a machine will take and will bond wires to a point on the silicon off to that leg, and that's what they call wire bonding. And this is an example of what we call a quad flat pack, something that has wires on all the sides. Some of them are on the bottom, called ball grid array. We'll actually look at that later. So you're left with this piece of silicon. Oh, and then to finish it off, they put a piece of plastic on the top so it's safe from being touched by human fingers. And then, of course, when you're done, then you put that on a board. Have you ever seen how they put stuff on boards? Yeah. I got a video of that. Let's go look at that. The video is of a small electronic board that I had made by a company locally. This is also available on YouTube. So I'll go to YouTube. Good thing I only put safe things on YouTube, none of these nasty videos. Oh yeah, the bottom one, my son had a lizard and he put it on a Roomba. All right. Here is an example. So what you have is a machine is picking up parts, this plastic, and it's putting it on a printed circuit board. And once it picks it up and puts it on the printed circuit board, it's held into place by solder. It's called solder paste. And it doesn't move much, but it's not done. And then the entire board is put through an oven, and the oven melts the solder, and then when it comes out, it solidifies. As another example, let's see. I could show this one as well. Start it all over. What's one thing you notice when this is doing it? What's that red light? The red light is an infrared light, which is actually showing up on the part. There's a camera in the middle that's looking at the orientation of this part. Because as this orientation of the part comes out, it could be twisted a little bit, and it wants to put it on the part exactly lined up. So that's how you would manufacture a printed circuit board. And here's an example of a printed circuit board that you might put something on. Gee, I wonder what that is. Glad I didn't look at that thing. All right. So, here's a good example right here. How to go a little bit further. You could show pictures of the printed circuit board. Somebody's trying to sell there. Here it is. All right, there we go. So as the part is placed on the board, you can see it's got the legs and it goes on top of the paste wire. All right. This is a good example of how you're going to manufacture an embedded system in general. Again, as we said, the wafer goes into the plastic. The chip, the plastic itself, will be put on some sort of PCB, printed circuit board, which then goes into something like a mobile phone. So it would be good if you understand this general concept of manufacturing. So, what I was going to say is, what do we put in here? What do we put on the cylinder? What do we put on the silicon? What's important? So what I would like you to do is to turn towards somebody else, and for a couple of minutes, what do you want to put on this microcontroller? Now, we talked about some of the things that you could put on a microcontroller. in the last class, right? And you've read the book, right? Yeah, like it. So I will randomly call 4 people to write on the boards on the side after the 3 minutes. So I give you 3 minutes to identify what you're going to put on the microcontroller silicon. Go to it. So turn to your next door neighbor, and between the 2 of you, write down what you think it'll be. You know, if you're in a group of 3, that's okay, but it's got to be no more than 3. So I see 2, 2, 2. No share. On the microcontroller. No, just microcontroller. Again, you're doing just the microcontroller chip. Just the chip. Not the printed circuit board, just the chip. What's going to be on it?
What is the question?
See, I'm really putting chalk around. You better get it done. I have to go steal chalk from another room. I'll keep working. All right, who's not done yet? Oh, good, everybody's done, so I can call on anybody. All right. So, the rule, I'm going to call 4 of you to the boards and you're going to write it on. You have to write your names on the board too in the corner. All right, and then you're going to write, guess what, choose. You 3 ladies. You get that board. Go ahead, go to it. You 2 gentlemen. You get that board. Ding, 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 the winner. You look ready to go. You get this board. Yay! You're the winners. You get this board. Oh, people up here, they think they've escaped. But no, I'm going to let you do the front. You're the winners. All right, come on over. You need more chocolate? You need more chocolate? None.
What are they?
Right here. What if I wrote that? That's small. By the way, Corey and Tyler, great. Nice size. Good. I can see it. Good. Is that it? You guys done? You didn't do the work? Oh.
You just want all the physical? Yeah.
What you want? So what I would like you folks that are out here looking at is what they've put up there. What's important? So here, I'll look at this one over here. All right? ALU, which stands for the alpha lovable unit, right? By the way, ALU, arithmetic logic unit, right? Oh, you know what? How good of a camera person are you? Can you turn that towards them? Here, I'll do it if you feel kind of shy. All right, let's turn the camera. There we go. Oops, don't want to fall. So we'll look at the alpha lovable unit. Arithmetic and logic unit says what? This is computer architecture, which you should have had before this, right? What does the ALU mean? All right, so it does the computation. It has registers. So it has all sorts of registers to get data from. It has control path and data path. It has adders, maybe a multiplier, maybe a floating point unit. Oh, we got timers. Remember we talked about that in the first class? Timer being some device that will be able to give you a certain time tick. Memory, well, that's also good to have, right? Now notice they have data and program. Do you want them separate? You don't want to have the same thing, right? All right. Notice they weren't specific on what the memory is, like what technology. Is it ROM, Flash, RAM, SRAM, DRAM, EEPROM, EEPROM, PROM, ADC and DAC, analog to digital converter, digital to analog converter. UART, we've already covered that, right? Universal asynchronous receiver transmitter. LCD driver, I like that. So a device that will, or something on the device that will actually say, this is what you need to show on the processor, or this is what you need to show on the display. I/O ports in general, that's pretty good so far. What do we have over here? Oh, this is, I'm going to have to show the video. This is where I'm going to get somebody watching the video kind of motion sick, all right? Here we go. All right, ladies, you're the winner. Here we go. We have, I'm going to have to zoom in on this one. Oh, zoom out on that one. All right, ADC, I've seen that before. I can't read that second one. Oh, input-output pins. Timers, oscillator. Here's something that somebody else didn't say. Oscillator. You know, it would be nice to have your specific chip also have the ability to control the timing of a specific, or to have the clock so you don't have to have additional capabilities over here. What do we have over here, gentlemen? We have the clock. They did it too. Power. This is the first person who mentioned anything about power. Would that be maybe a converter? All right, here we go. We have more timers, I/O ports. And up front we have Multiplexer, I/O, ALU, I've seen that already. Good, good. So why did I have you do this exercise? Thank you. You can all have a seat. And you know what? You can have a trip to all of you can have a trip to the prize closet. But you're going to have to come to my office to look at the prize closet. Why did I go over this? I went over this because when we're working with the microcontroller, look at all these things we're going to have to access. So we're going to have some protocol or some rules for how to access everything. Probably most important is, how do we access the memory? Now, hopefully you all have had computer architecture, so you know the general concept of an address and the contents, right? So you already know how to access memory. One trick we often do in the world of embedded systems is we actually say, hey, let's just access the ports in the exact same way. So we treat it like a memory address. And while we're at it, why don't we do the same thing with our A to D converter? And we do the same thing with our I/O ports, ADCs, not the ALU, the ROM, RAM, UARTs, LCD drivers. All of that, what we could just say is treat it like memory. When we put some data into a memory address, that means that we are going to want that data in that memory address to do whatever it has to do. So if it's a UART, you put the data in that memory address, then the hardware takes care of sending that out the UART. You don't have to worry about actually sitting and giving it a clock to send everything out one bit at a time. You put it there, whoop, it's gone. There are even some devices that you can put maybe an entire 1K into a single buffer. I've seen that around here somewhere, the word buffer. So you put an entire 1K of memory that you want to be sent out via a port, a UART or some other port like that. And then the hardware takes care of sending it all out, and then you being the software that's running the embedded system, can do something else. So this is a concept that we often call memory mapped I/O. On camera. So in memory mapped I/O, again, the concept is that you will have a specific location, and this location we often call a register. Now this is different than the typical register that you may be associated with an arithmetic and logic unit. Now if you've had computer architecture before, which I think all of you have said you have, remember you refer to different registers that is associated with the ALU, or the real nitty-gritty, the insides of the processor. You might have an address register that is A0 and A1 and A2, or a data register that might be called D0, D1, D2. Or maybe something else called the stack pointer, or maybe something else called the frame base. There's a whole bunch of different names. Oh, some of the bigger ones. What's the biggest one? What's the most important register?
Control and status.
Yeah, PC. Program counter. So you know what the next instruction you're going to execute. And what's the second most important one? The flag register, flags. Remember, the flag register is that which identifies, is one thing bigger than the other? Is the register 0? Is it positive? Is it negative? We're also going to see some examples of this associated with things like, or concepts like overflow, interrupts. So you're going to see a lot of the different types of flags and error conditions come up when we start working with programming the embedded system. Somebody up here said something along the lines of parity. And actually that is, when we're looking at some of the registers associated with I/O ports, UARTs and such, then we're going to start having flags like that, like overflow and even parity, detected odd parity errors, things like that. So, going back onto our processor, one thing that I saw a lot of too is I/O ports. So again, when we talk about I/O ports, we're going to use it with respect to memory addresses. And in particular, we're going to interchangeably use ports with register. So when we talk about it, we're going to talk about something like a data direction register as well as a data register. Man, I gotta get better handwriting, don't I? And so, what we are worried about is if we're sending anything out to an outside I/O pin, an I/O port, we have a really great advantage. Our pins here could be both an input and an output, but not at the same time. I mean, it could either be an input at one instant at a time or an output at one instant of time. And it could switch, but you have to tell it which way it's going to go. So it's either going to be input or it's going to be output when you work with it. And so for us, we will have a data direction register. And by the way, this is DDR as an example. DR, if we're talking about something. And I would want to point out that what you can see on a specific pin might be, hey, maybe this is port 4, pin 0. Port 4, pin 1. Port 4, pin 2. Port 4, pin 3. All the way down to port 4. Did I say bin? I meant to say bit. All right. Port 4, bit 7. So that would turn out to be a register. And again, the way we work in our numbering is that this is bit number 0, 1, 2, all the way up to bit number 7. That would correspond to those particular bits. But we need to identify which one is going to be input and which one is going to be output. So on each one of these pins, we might put a voltage. Now, if we say that this is a digital port, what does digital mean? 0 or 1. All right, so 0 is equal to 0 volts, right? Ground. And logical 1 refers to, we'll call it generally VCC, because it all depends on the board, the manufacturer. That processor will run at anything from 5 volts, 3.3 volts, 1.8 volts, and they're getting even lower. Again, why is it good to have lower voltage? Power consumption, less current, less heat, mostly less power consumption, more efficient. But what's the big problem with lower voltage? It gets a lot more sensitive to noise and other things going on in the system. These are all concepts that are also important for an embedded system designer to know. They need to know not only what voltage you're running at, but they also need to know the voltage of the signals, any filtering of the signals that are going on. By the way, has anybody ever heard of something called a pull-up or pull-down resistor?
Yes.
All right. Pull-up and pull-down resistor is there to identify a specific pin as being normally a certain voltage. So in this case, let's say we were to put a pull-down resistor. That means that we would put an extremely large resistor value, sometimes 10 k ohm. And that means that that pin would normally be read as 0 volts. And when some device over here would put a voltage over here, VCC, you would have a current draw from here, but this would still remain VCC at this point, which is logical 1. And when whatever the source is right here would then drop it down to 0 volts, of course, this point over here would be changed to 0, logical 0. And the nice thing about a pull-up and a pull-down resistor, and this is a case of a pull-down resistor. The nice advantage of a pull-down resistor is that this pin does not float. We're going to see a little bit later an example of where we want to ensure that we have this always pulled up or pulled down, but the neat thing is that most microprocessors or microcontrollers have that built in, that it's already there available for you to use. So let's get back to my example here. If I have all of these pins, and I were to put the voltage equivalent to 0, 1, or actually it would turn out to be, in this case, let's see if I can get this, 3, 4, 5, 6. Did I get all the right 1, 2, 3, 4, 5, 6, 7, 8? All right, so what would my pattern be if I wanted to read, and this is port 4. What would I read if I said, tell me what port 4 is? It would be 1, 0, 1, 0, 1, 0, 1, 0, right? Because that's the supposed voltage going on each one of these. We'll go back over here to beam 1, right? Hex AA. And if I wanted to read this, then all we would need to do is say, oh yeah, this has a specific name. And what is the name of this specific port? So as it turns out in our example, we would call this port 4.dr, and that would be identified as our specific entire byte. And I'm not going to go today into the definitions of the structures, but that is what we would want to refer to it as the entire byte. By the way, we would also have to say byte. Any questions? I hear murmuring. Now, what that means is that we now have an identified name for that particular set of pins coming in to our chip. And at any time, we can actually take this hardware phenomenon, read it in, and convert it into software. And so what would we want to do? We would want to write some code to put it in place. So let's say we had a variable int x, right? This is C, and I'm going to be using C for this class. How many of you out there have a good knowledge of C? Raise your hand high, I need to know this. All right? How many of you are kind of weak in C? How many of you know absolutely nothing in C? And I didn't see any of you guys here raise your hand for anything, all right? So, would it be worthwhile for me to go over C in the next class? Or do you want to learn it on your own? All right, I will cover it in the next 2, maybe 3 classes. Because this is important enough, because the whole rest of the semester you're going to be running your labs in C. And if you don't understand it, whoa, you're going to be in big trouble. So, let's assume that at least you know this, all right? We're identifying an integer. An integer is we'll call this at this point a 16-bit number. So what I'm going to do is I'm going to show you a little bit of C that I will expect you to understand, and then we'll take it apart. So if I want to read in whatever is in port 4, I will say so, read the 8 bits, that's what this first thing here says. Read the 8 bits, which is port 4 data register. Read the 8 bits, convert it into a 16-bit integer, and then store it in the variable x. So this is a concept here called casting. So I am casting a byte into an integer value. Why do I want to do that? Right? What I want to do is I want to be specific and let the compiler know that I do realize that this data coming in is going to be a byte, that it's supposed to be 8 bits. But those 8 bits are going to be stored in a space that's 16 bits wide. And I realize that, so what it will do is it will make sure to allocate 16 bits and just make up the top 8 bits. And what it makes up of the top 8 bits are typically zeros, but I'm going to go into that in more detail later. Now, one thing I didn't mention here is, hey, you know what? That could be an input or an output, right? So maybe I need to identify which direction is it going to be. Is it going to be an input or is it going to be an output? And this is where I always mess up. So if I don't do it right, you have my permission to yell at me and say, you didn't do it right. So if I want to make this an input, what I do is I identify also that port 4, the DDR, data direction register, right? That byte is going to be equal to 0x, meaning that I'm going to give it a hex number. By the way, what is input? How do you define an input for that particular pin? Zeros. All right? So if I said 0, 0, I'm going to make it really nice and pretty. I'm just going to say 0, 0. Even though I could just put 0 in there, and it would do the same thing. So that means that I am going to identify port 4 is input. And oh, by the way, that's the default. And if I wanted to make an output, then I would make all of that. So I'll give one example here. I'll say port D.DDR. If I wanted to make this all outputs,
A7.
So what I have done is FF is hex for, of course, 1111, and I've identified everything as output. Notice I'm starting to use hex and stuff like that. It is assumed you already know what that is. All right? If you do not know all the hex, if you do not know all of the hex numbers, whatever, you have until Monday, because you never know if I'm going to come up with a quiz that asks you to give me some stuff on hex. All right? So brush up on your hex. That should have been covered in your digital logic, computer architecture, all the previous classes, all right? So again, I've spent a lot of time here going over some stuff that might have been new, some stuff that should have been old. So how many of you thought today's lecture was a little bit too basic? All right? How many of you said this was about right? How many of you think that this was maybe a little bit too fast? Nobody's going to raise their hand, right? All right, so again, the first 2, maybe 3 lectures are going to be rudimentary stuff, but after that, we're going to start going a little bit faster. Thank you very much.